we're going to take another pause today and talk again about interpreting confidence intervals because I think this is really important and kind of regardless of what type of model you're fitting, if you're trying to do inference, you're going to be needing to calculate confidence intervals and interpret them for your beta coefficients or for your parameters from your model. And so understanding what this means is really crucial. And I've just been noticing in some of your written responses that the understanding of kind of what these confidence intervals, how to actually interpret them once you have numbers in front of you, is challenging. Which it's a challenging concept, and part of this has to do with kind of how these are taught along the way, because sometimes I think they're not taught in a way that's really clear. For example, I know a lot of times it's taught as that we are 95% confident that the true value falls between, X and Y. And that word confident has a lot of baggage to it. What that word confident actually means, it does not mean that 95% of the time the true parameter falls within, the limits X and Y. It means this more complicated kind of description where it talks about the procedure that was done and the percent of the intervals calculated using that procedure that would contain the truth. And so because I think that wording sounds very simple but includes this word confident that has some baggage behind it, there's sort of some work to undo that thinking. And so I wanted to today kind of slow down once again and just really dive into what a confidence interval is. I'm going to show you kind of via some simulations what it is in these slides. And then I'm going to walk through actually programming this in R so that you can run these simulations yourself. And then you're going to run the simulations in the application exercise. And then finally, you're going to write up basically what you've learned from this. And hopefully this will sort of help solidify what this means, what a confidence interval means. Okay, so the definition of a confidence interval. If we use the same sampling method to select different samples and computed an interval estimate for each sample, we would expect the true population parameter, for example, beta 1, if that was what we were estimating, to fall within the interval estimates 95% of the time. What is this not? This does not mean if you get a 95% confidence interval, for example, from 5 to 9, this does not mean we would expect the true population parameter to fall between 5 and 9 95% of the time. This is not correct. No, not right. And I'm seeing this a lot, and it's very common. This is a very common misconception of a 95% confidence interval, but it is not what it means. So let's cross that out. Why is this not what this means? Well, first of all, it's not what actually is being described by a confidence interval. But an important piece here is that the true population parameter is fixed. So it's not possible for the true parameter to fall between some range a certain percent of the time because that truth is fixed. So it's either always going to be in that range or never be in that range, but it doesn't fall within that range with some probability. So the true parameter is fixed. And let me clarify that when I'm saying the true parameter is fixed, I'm saying when we're talking about confidence intervals as you've learned them in this class, which rely on what's known as frequentist theory, the true parameter, so the beta coefficients, for example, are fixed. Now, if you end up taking a Bayesian inference class, which Bayesian inference is sort of a different way to think about statistical inference, and when you do that, you're going to learn about something called credible intervals. And credible intervals are somewhat similar to confidence intervals, but they have different underlying assumptions. And so what we're talking about are the confidence intervals that you typically see when you run any kind of regression analysis, or really actually any analysis that would output kind of parameter estimates for a model. Those confidence intervals are what we're talking about here. So in this setting, the true parameter is fixed. And so there's not like a probability of that truth falling within some interval because, if the true parameter is 4 and the interval you saw is 5 to 9, 100% of the time 4 is outside of 5 to 9. If the interval you saw was from 3 to 6 and your truth is 4, 100% of the time 4 falls within 2 to 6. So you don't think about these as in terms of the probability of the truth. You think about these confidence intervals in terms of the probability or the proportion of all of the intervals that could potentially be calculated using this same sampling and estimation technique that would contain that truth. So it's sort of a different way to think about what that probability is. Okay, so to drive an example, we're going to pretend like we know some truth. And so let's say we're interested in the relationship between age and wage. So the relationship between how old you are and how much money you make. And so to demonstrate what a confidence interval is, I'm going to construct a truth for the relationship between age and wage in some made-up land, some Lucy land. And so in this land, you always make 2 times your age. That's how much money you would make, plus some error. So this would be the relationship, the true relationship between age and wage. And so what is the true parameter for the relationship between age and wage? It's 2. So this 2 here is the truth. This is my beta 1 here. This is the true relationship between age and wage. Okay, so I'm assuming that age here in my true Lucy land, age is normally distributed with an average or a mean of 30 and a standard deviation of 10. And my error term here is also normally distributed with a mean of 0 and an error of 10. And I'm going to sample 100 people from this true distribution. So this is the truth. These are some operating characteristics or some characteristics of the true kind of population here, and I'm using this to be able to sample from this true distribution. So you could imagine that I have this true kind of infinite population of people that have certain ages and certain wages, and I want to try to estimate that relationship. We happen to know the truth because I've told you it's defined as 2, but let's say we don't know the truth and we want to just estimate that from a sample. So if I were doing this in practice, I would sample 100 people, and I would measure their wage, and I would measure their age, and then I would try to quantify that relationship. And so in R, I can do that by, I'm setting a seed here just so that we get the same answer each time. And I'm setting my sample size here, n to 100, and I'm generating this sample. So this is going to be a data frame, and I'm going to have age here. And what R norm does is it's a random normal. So this pulls a random normal variable. It pulls n of them, so in this case 100. And this random normal variable is going to have a mean of 30 and a standard deviation of 10. So I'm just pulling 100 people from my population, and these are their ages that I've pulled. And now I'm going to calculate the wage for this, and I know from my true distribution that this is going to be 2 times their age plus that epsilon term, which is just going to be a random normal with a mean of 0 and a standard deviation of 10. So that's what this is. So now I've calculated that wage variable. And so now I have my sample. I have a whole bunch of ages and a whole bunch of wages. If I looked at the whole data set, I would have 100 of each of these. I'm just looking at the first 6 just so you can get an idea of kind of what this is. And as you'll notice, age is approximately half of wage, or wage is 2 times age, which is the relationship we would expect. But it's not exactly because we've got this error term here. Okay, so this is my sample. Let's say we did this again. So we're going to set n to be 100, and now I'm going to generate a second sample. And so this time, I'm again going to pull from a random normal distribution. I'm going to pull a different 100 people from Lucy land. And these people, their age is a mean of 30, has a standard deviation of 10. I'm going to calculate the wage in this second sample. It's 2 times their age plus this random normal error term. And so comparing sample 1 to sample 2, they look pretty similar, but obviously they're different. So here, my first 6, they have ages 52, 18, 23, 25, 20, and 20. In my second sample, my first 6 have age 50, 38, 29, 36, 42, and 18. Okay, so now this is if I had 2 samples. And so what are we doing? The purpose here is we're going to fit a linear model on the sample. So this is the linear model that I would see. Often you only have 1 sample from your true distribution. And you fit some linear model on that sample, and you get an estimate for age. And so here on this sample, I got a pretty close estimate to the truth. I got an estimate of 2. And I got a confidence interval with a lower bound of 1.81 and an upper bound of 2.208. So that's my confidence interval, 1.81 to 2.21. So this is the linear model for my sample. How do I interpret this confidence interval? So what percent of the time does the true parameter fall within this interval? In other words, what percent of the time does 2 fall within this interval? Well, 2 is our true parameter. 2 is a fixed number. 2 is always going to fall between 1.81 and 2.21. So it falls within this parameter 100% of the time. That's kind of a meaningless estimate. What we actually want to know is if we were to repeat this process many, many times, how often would we capture that truth or that 2? So let's look at sample 2. I fit the linear model on sample 2. I end up with this estimate. Here I end up with an estimate of 2.078 on this sample with a confidence interval from 1.89 to 2.27. So this is my second confidence interval. What percent of the time does 2 fall within this interval? Well, again, 2 is just fixed, and so this is not really a meaningful estimate. It falls within this estimate 100% of the time, but that's not really what we're interested in. What we want to know is if we were to do this a whole bunch of times, what percent of those samples would capture the truth, or what percent of those intervals would capture the true parameter? And so here's my interval, my first interval from sample 1. Here's my interval from sample 2. Both of these captured the truth. But what if we did this a whole bunch more times? So let's say we do this 10 times. So here's my sample 1 again, my sample 2, and now I did this 8 more times, and so I've got 10 pulls from this data set. What's my confidence here? Well, actually, it's still 100% because with these 10, it turns out that every single time our interval contained 2. That's pretty good, but 10 is really not representative here, so let's look at a couple more. So what percent of these intervals contain the true parameter? Well, 100% in this particular case. But if we look at 50 samples, then we start to see a couple times where the true parameter 2 is not contained in the interval estimates. So in this case, it happens 2 times. We've got 2 intervals that were calculated on samples generated from this true distribution where they didn't contain it. And that was just by chance. When we sampled, we just ended up getting a couple that just didn't quite match that true distribution. So what percent of the intervals here contain the true parameter or contain 2? Well, it'd be 48 out of 50. So the black lines, there are 48 black lines out of 50 total. And so that's 96%. So 96% of these intervals contain the truth. So that's pretty good. Now, if we do this 100 times, then we start getting closer to what we would really expect because we know this is a 95% confidence interval. And so if I did this 100 times, I end up with 5, 1, 2, 3, 4, 5 that fall outside. And this is exactly what a confidence interval is telling us. It's telling us if we were to repeat this sampling procedure lots and lots of times, we would expect that about 5% of the intervals that were calculated would miss the truth, would miss that true value of 2. But we would expect that about 95% of them would capture the true value or would capture that truth. So when I'm looking at just one interval, which is what you often have, and I'm looking at just one of these lines in just one of these samples, we can't say anything about whether or not what the probability is that that interval contains that true value. That's not what we're capturing because that truth is either inside that interval or it's outside that interval. It's possible that I am looking at this interval, and it's also likely or possible that I'm looking at this interval. And I don't know which one I'm looking at, so I don't really have a sense of what the probability is that 2 is within the interval that I'm observing or not, because I don't actually know the true value or that 2 to be able to make that assessment. But what I do know is if I were to repeat the same procedure on different samples that are drawn from the same population many, many times, I know that 95% of the intervals that are calculated will contain my truth. So it gives you some confidence in the procedure that you're doing. So the correct way to interpret a confidence interval is you can state what that confidence interval is. So the confidence interval for the coefficient for age is 1.8 to 2.2. And this means that if we were to repeat this process many, many times, we would expect that 95% of the intervals calculated would contain the true parameter for age. So what I want you to do is I want you to watch the next video where I code this up. So I'm going to show you exactly how to code this simulation up. And then I want you to either code along with me, so either pull up your R Studio like next to my video so you can code while I'm coding, or if you'd like to just watch through the video and then repeat the same steps afterwards. Essentially, I want you to build an understanding of what these confidence intervals are.